Hello everybody, welcome to week 2 of Calculus Online. For this section, we're going to be talking about indefinite integrals as opposed to definite integrals. So before we were working with definite integrals, meaning that we were getting a numerical value at the end. We were looking from A to B and evaluating. So we were finding the antiderivative at B and subtracting the antiderivative at A. So every time we were getting some sort of number. Well, in this case, we're looking at indefinite integrals, so we don't quite have a number. Instead, we're going to get a function at the end. And because we're going to get a function at the end, we have to have my favorite thing, plus c. You have to have that plus c at the end. Okay, so looking at this section, it's nothing out of the ordinary. It's all stuff that you know how to do. You know how to find antiderivatives. It's just making sure that you have the notation correct and you're using plus c every single time. So we have this definition here. We know that this long stretched out s means integral. So we're integrating the function f of x. We have that dx at the end. Remember, that's important because it tells us what we're integrating with respect to. And that equals the antiderivative at x. And remember, whenever you have an antiderivative and it is a function, right, you have to have plus c. So that's the most important part. So then they give the definition, so they're showing that capital F of x just stands for the antiderivative. So when you take the derivative of the antiderivative, you get back to the original function. So they give us a nice example here. So they have the integral of x squared dx. All we do, since it's a power, we can use our power rule where we add 1 to the exponent, so that 2 becomes a 3, and then we divide by the new power. So you're dividing by 3, and then you have to have, I will cry if you don't have plus c at the end. And then you can always double check yourself. Remember, d over dx, that's a different notation for taking the derivative. So you're taking the derivative of the antiderivative and you should get back to the original function, and you do. Alright, so continuing on, we have the antiderivative of secant squared x. So if you think back to when you were taking derivatives, you know that the derivative of tangent of x is secant squared x. So the antiderivative of secant squared x is tangent x. And what do you always have to have? Plus c. So then double check yourself by taking the derivative and you get back to secant squared x. And remember that plus c represents a constant value. So they have a nice table here, and this is a great study guide. So it has the table of indefinite integrals. So let's go through this all together. So we have the antiderivative, or the integral of a constant times a function. We can bring that constant on the outside. So let's say we have 5x. We can bring that 5 on the outside. So that's one of our rules. Over here, we know that if we have addition or subtraction, we can split up those two integrals. We have the antiderivative of a constant. All we have to do is tack on an x and plus c. Take the derivative and you get back to the constant. So that's good. Adding 1 to the exponent, dividing by the new power. That's one of our faves. 1 over x is a common one you'll see. It's ln of the absolute value of x. The reason why they have absolute value is because you can have plus or minus x and still get 1 over x. The derivative of e to the x, another common one that you're going to see. So the antiderivative of e to the x is e to the x. Similarly, the derivative of e to the x is e to the x. That stays the same. Don't get e to the x confused by if it was just e. If you just have the value e, then that's a constant, so you're using this rule up here. But e to the x is a function, so that's why we have e to the x plus c. This one's a little less common, but still good to know. So we have b to the x, and I think you probably proved this last semester when you were doing derivatives. There's a proof for this. I'm not going to go through it, but the integral of b to the x is going to be b to the x over ln of b plus c. And then these are all very important rules. We have sine, cosine, secant squared, cosecant squared x, secant x, tangent x, cosecant x, cotangent x. So this is all your trig functions, and you should be familiar with almost all of them. Some will be used more commonly than others. Sine and cosine, of course, you're going to see that all the time. These are a little less common, but you're still going to see it quite often. And then we have some more trig that you should be familiar with. So these are some of the, you won't need to know the last two. We won't really discuss cosh and stuff like that, so you don't need to know these ones, but be familiar with these two. So inverse tangent and inverse sine. Alright, so continuing on, they have another example. So they have the integral of 1 over x squared. So they skipped a couple steps, but remember you can rewrite this as x to the negative second. So when you add 1 to the power, it becomes x to the negative first, and you're dividing by negative 1. X to the negative first is the same as 1 over x, so we have minus 1 over x plus c. This is our first big example. So we're integrating 10x to the fourth minus 2 secant squared x dx. So real quick, think about what trig functions you know, because we have secant squared x. So is there something that when you take the derivative you get secant squared x? And of course that's tangent of x. Okay, so they split it up into two different parts. You don't have to do this, but it does make some functions a little easier to find the antiderivative. So they split it up as they brought 10 to the outside and they're integrating x to the fourth dx minus 2. Since 2 is a constant, they brought it up the outside, and they split it up into two integrals. So we add 1 to the exponent, x to the fifth over 5. Secant squared x becomes tangent x, then you have that plus c. So this becomes your final answer. And they give you a note. You should check this answer by differentiating it. So that's always a great thing to do, checking your work. You can also check it by graphing if you're familiar with what the graph should look like of derivatives and antiderivatives. Alright, so now we're getting into cosine and sine. So we have cosine theta over sine squared theta, and we don't have a rule where we're taking the antiderivative quotient rule. We don't have that, so we have to rewrite this using some algebra. So what's cosine over sine squared theta equal to? Well, we can split it up into 1 over sine theta times cosine theta over sine theta. 1 over sine theta is the same thing as cosecant theta. Cosine over sine theta is the same as cotangent theta. And looking back at your antiderivatives, cosecant theta, cotangent theta, the antiderivative is minus cosecant theta plus c. And again, you can check this using the antiderivative, taking the derivative of the antiderivative. And you get back to cosecant cotangent theta, which is what we want. All right. So now for example 3, you have to think about, is this going to give us a number or is it going to give us a function? So we have bounds on this one, so our final answer should be a number. And I think this actually was an example when we were learning how to evaluate definite integrals before. So we already went through this example. We have to plug in those bounds and we get a numerical answer. All right, so for this one, are we going to get a number or a function? Again, we have bounds, so this is a definite integral. And remember, we're looking in terms of area. So we know we're going to get a numerical answer for this because we're looking from 0 to 2. So we're going to get a numerical answer. Well, first we have to find the antiderivative, and this one's a little trickier. But if you look back at your rules, we know that the first part's going to be 2x to the 4th over 4. That's pretty easy, just adding 1 to the power, dividing by that new power. We have minus 6x squared over 2. Again, that's the same rule. This is where it gets tricky. Remember that 1 over x squared plus 1, the antiderivative of that is inverse tangent. So just bringing that 3 to the outside, we have 3 times inverse tangent x. And we evaluate from 0 to 2. So first you plug in your 2 everywhere, and then you plug in your 0 everywhere. And that's how you would get your final answer. In this case, when you plug in 0, you're just subtracting 0. But if it wasn't 0 at the end, you would have to make sure that you distribute that negative to each part. All right, and remember we're looking at net area. So over for this example, this is another good one. I think there was something similar on the exam to this problem where you have to split up this into different fractions. So this function will be split into 3 different parts by just putting it over t squared. And then once you simplify it like that, it's a lot easier to take the antiderivative. So the first part becomes 2, second part becomes t to the 1/2, because that t squared over t squared cancels. The last part, it's minus 1 over t squared, so it's minus t to the negative second. And then you just use the power rule for each of them. Plug in from 1 to 9. So first you plug in 9 everywhere, then you plug in 1 everywhere, and in this case we don't get 0 at the end. So look how careful they are with placing the parentheses. Remember, we're subtracting all of this function at 1, so they have parentheses. Alright, so finishing off this example right here, we're just evaluating, so plugging it into your calculator or doing it by hand, either way, and you get 32 and 4/9. So that's how you would get that answer. So really this section is about distinguishing the difference between indefinite and definite integrals. Alright, so continuing on, we're looking at applications. So this is probably the main point that I want to get across in this section, is the different applications of evaluating and finding these antiderivatives. And remember, it's really talking about area. And there's one particular problem that I'm going to go over because I don't think they explain it that well in the textbook, and I want to make sure everybody's okay with it for the exam and for upcoming quizzes. So they talk about the net change theorem, and it's basically just what we had before. We're just taking the antiderivative from a to b, so integrating with a to b, and subtracting the upper bound of the antiderivative minus the lower bound of the antiderivative. And there's this nice video if you want to go ahead and watch that for extra practice. It talks about the net change theorem, but it's just applying what we already know. So the net change theorem, remember, we're finding area, but it's the net area when we're integrating. So we'll look at an application of this, and I think it'll make more sense. So some of the examples that they give that you might see, if we're talking about volume of water, then its derivative is going to be the rate at which the water flows into the reservoir at time t. So it's a change in the amount of water in the reservoir between time 1 and time 2. You can also use it for chemical reactions and looking at those times, so the difference between time 1 and time 2 again. You can look at the mass of a segment, rate of growth of a population. Marginal cost is another application. So it's pretty similar to the different applications that we've seen for derivatives, except it's a little different of a take on it, where we're doing the opposite. So instead of taking the derivative, we're taking the antiderivative. So then this is a main point that I want to get across, is the velocity one, because this is the most common one that we're going to be using in this class in particular. The one important part of this is knowing the difference between displacement and distance. So I actually have a nice example that I think demonstrates visually the difference between distance and displacement, and I'll link this in the discussion so that you can refer back to it. So if I'm walking and I'm going on a long walk and I'm going all the way around this path and I end up at this point, my distance is how far I traveled, right? All the way around. The displacement is different because it's wherever you look from the starting point to your end point. So it's this path right here. So if I ended up walking all the way around this distance, and let's say I ended up back to my starting point, the displacement would be 0, whereas the distance would be however far that I walked. So that's the difference between the two. And this website actually takes you through more in depth if you're still confused about that. And then they talk about right here. So the net change in position is the displacement. So that means when we're integrating, we're just going to integrate as normal to find the displacement of our object. So if we wanted to calculate the how far the object travels during the interval, so instead of just taking the net change of position, we want everything to be positive. Because remember, when you're graphing stuff, if it's above the x-axis, then it's positive. If it's below, it's going to be negative. So that's why we want to make everything below positive as well, because we want to know the total distance traveled. So pretty much you're looking at the absolute value of the function. So right here, total distance traveled, we're looking at the absolute value of the function. Alright, so looking down below, this gives us a visual representation. We have A1, A2, A3. Remember, A2 is going to be negative. So if we're looking at the displacement, we're subtracting A2. But if we're looking at the distance, we're adding everything as a positive value. Okay, so this is the example that I wanted to talk about, and let me know if you have any questions about this example, because this is probably one of the most important applications that I want you to mainly focus on for this section. So let's say a particle is moving along a line so that the velocity at a time t is given as this function right here, t squared minus t minus 6. And we're in meters per second, so our answer is going to be in meters. So find the displacement of the object of the particle during the time period from 1 to 4. Okay, so 1 to 4, that's 1 is our A, 4 is our B, and we're just integrating as normal because we're looking at the displacement, and displacement gives us the net area. So integrating as such, we just add 1 to the exponent divided by that power. So we get t cubed over 3 minus t squared over 2 minus 6t. We're looking from 1 to 4. So when we plug in 4 everywhere and subtract the value that we get at 1 everywhere, they end up getting minus 9 over 2. They didn't show the step where they plug it in, but that's how they get their answer. They're plugging in 4 first, and then they're subtracting, plugging in 1 everywhere. And you can double check that as well in your calculator. So then, the trickier part is when we're finding the distance traveled during this time period. So to find the distance traveled, we want to make v of t positive everywhere. So how do we do that? Well, we have to figure out where it's negative in the interval from 1 to 4. Because again, that's what we're looking at, from 1 to 4. So we want to know where it's negative from 1 to 4. Well, to do this, we want to know where it's equal to 0. And then similarly, you can check values in between. Once we have those 0 values, you can check values in between each of those to try to figure out where it's positive and where it's negative. So t squared minus t minus 6 is equal to t minus 3, t plus 2. So we know v at t is going to be 0 at 3, and it's going to be 0 at minus 2. So then we're checking values between 1 and 4 to see where it's positive and where it's negative. So if we test values between 1 and 3, because that's our first critical point, is at 3, sorry, not critical point, but value. It's our first 0 is at 3. Then we end up figuring out that v of t is negative. Because let's say we plug in 2, we have a negative times a positive, so it's going to be negative. But v of t is positive from 3 to 4. So plugging in 3.5 everywhere, we get a positive times a positive, which is a positive. So that portion's going to be positive. So we don't have to worry about that as much as this first part. So going down, we can split 1 to 4 into 2 different parts. So we're looking from 1 to 3 and 3 to 4. So you might be wondering, why am I not worrying about that -2? Well, -2 isn't in the interval from 1 to 4, so I don't have to worry about it. So we split up our integral using our zeros. So we're looking from 1 to 3, 3 to 4, and we know together it's going to be from 1 to 4. Okay, so then we have minus v of t dt and we know that this is going to be minus. Why do they have it negative? Well, because this value right here, so from 1 to 3, it's a negative value. So they put a negative sign when they write it to make it positive. So remember, v of t is negative from 1 to 3. So if we have a minus sign here, a minus times a minus is a positive. So now we have a positive value from 1 to 3. I hope that's clear, because it's kind of confusing that they have a negative, because you think, oh, why are they making it negative? Well, they're putting that minus sign so that this function becomes positive in the long run. Because we know it's going to be negative from 1 to 3. I hope that's clear. And then we're looking from 1 to 3, and we have minus the function. So they just distributed a minus everywhere. This is going to be just the regular function. And then they evaluate. So t cubed over 3 with that minus sign plus t squared over 2 plus 6t. And they plug in values from 1 to 3. So they plug in a 3 everywhere. And then they subtract, plugging in a 1 everywhere. Over here, they plug in a 4 everywhere, and they subtract, plugging in a 3 everywhere. And that's how they get their final answer of 61 over 6. So another way to do this is by graphing. So you can check the graph to see where it's negative and where it's positive. If you're not comfortable with finding the zeros in that way, you can always graph the function and see where the zeros lie and see where that function is under the x-axis, where it's above on that interval. So I hope this is clear. If you have any questions, especially on this example, let me know. But that's the main points that I want you to get from 5.4. There's always additional exercises if you want to practice those. For this week, just a quick reminder, there's a quiz that'll be due on Saturday. This discussion post is going to be due on Saturday. If you need more time, just let me know. I know it's hard with all the different stuff going on, and working from home is sometimes hard, and keeping up with all of your classes that are online. So I completely understand if you need more time on anything. WebAssign, similarly, it's due on Sunday, but if you need more time on it, just let me know. I'm going to post this distance versus displacement for you guys, and then I'm also going to have you use these flashcards to study your antiderivatives. But other than that, that's all I have for you. Thanks for watching. I'll see you next time.